so today we're going to do, this is day 22. We're going to go over homework 5, which I think everybody did a pretty okay on, but there's a couple that I want to talk about for a concept. This is a lot more conceptual of a homework than previous ones. Then we're going to talk about MHD waves. And I'm going to talk about Alfvén waves, and I'm going to talk about fast and slow waves. So he talks about the existence of these other waves. I'm going to actually tell you what they are and where they come from. So we are nearing the end of the semester. So there's only one full week of instruction left, because I don't see the last week as a full week of instruction. Can't do anything on the last day. So the last day of class, we'll go over homework 6. I'm going to post homework 6 Thursday. I apologize for giving you a homework over Christmas break, or over Thanksgiving break, but I'm giving it to you way in advance. So there's a bunch of stuff that there's 2 things that are due after Thanksgiving break. Nothing's due after Christmas break. That was the way it was set up when I was in high school. We would go to Christmas and then come back and do finals. It's the worst way to do things. I don't know who thought that was a good idea, but
my sister's school just restarted that.
Yeah, restarted it.
Restarted it.
That's because somebody who's not a pedagogue was in charge. Some bureaucrat somewhere who made that decision. It's terrible pedagogy. Anyway, so Thanksgiving break is coming up. So we've got 2 lectures this week. So we'll talk about MHD waves, and then we'll jump to reconnection. Although I realized as I was writing down my notes, I'm skipping a couple of things in chapter 14. So it's possible that I changed my mind about reading 8 and I decided not to do dynamo theory. However, it is posted, so as of now, we'll try to go through where magnetic fields come from. Mostly because I think it's a very interesting topic, because we have these giant magnetic fields in the universe. The sun is very magnetized. The earth is magnetized. It keeps the atmosphere in place. And all of those processes are driven by a dynamo, which is turbulent motions giving you magnetic fields. So it's kind of my favorite stuff. It's turbulence and magnetic fields at the same time. So if I can do some dynamo, I will. But we'll see how the rest of the stuff goes. So there's a reading due tomorrow on reconnection. Don't get too bogged down in the math. Read it like a novel. I'm not going to ask you to do any of the heavy math. But the easy math, the reconnection stuff, the simple math, I will. So we'll talk about what I want you to do and don't. So we'll do reconnection tomorrow or Thursday, and then next Tuesday we will have class, even though it's Thanksgiving week. We'll do probably reconnection and start the dynamo, and then the following Tuesday we'll talk about dynamo some more, and then we'll finish up the homework and review for the final. So what's right now? Right now is looking at the homework. Where is it? Hydro. All right, should I plug it in up here? Would that be helpful? I don't know, I'll try it. So the first problem is random walk processes are governed by diffusion. And I am not going to go through all the calculus, because watching me do calculus is not particularly useful. But I will tell you how to do it. And I can't remember what's in the solutions. I'll make the solutions not totally worthless. So the first problem. It's up there now. Okay, so the random walk processes are dn dt equals some diffusion coefficient times d squared and dx squared. So there are a couple of different physical processes that like this equation. So this is the heat equation. This is diffusion of a contaminant. I think I spelled that right, but you can't read it, so it doesn't matter. So the question is, so let's see. So the first thing I asked was, show that n equals 1 over, okay, I'm going to try to do this off the top of my head. 2 pi dt square root of that e to the minus 1 half x squared over 4 dt. I missed a 4 in there, didn't I? Yeah. That's not 2 pi, that's 4 pi. And there's not a 1 half, there's just a 4. Okay, so show that this is a solution to that equation. 2, show that x squared equals 2 dt. And 3, pretend this is a heat equation, sketch the solution. So the first one, I'm going to tell you how to do it, but I'm not going to do it because it's not fun to watch me do calculus. So d by dt of this, 1 over 4 pi dt square root of that, e to the minus x squared over 4 dt. So you take the time derivative of this, and you get something. There's 2 terms in it. So there's a term that goes like this times this, and a term that goes the derivative of this times this, and a term that goes like the derivative of this times this. So you get 2 terms out of that. Then you take the second derivative in space. 4 pi dt e to the minus x squared over 4 pi, nope, not pi, 4 dt. And you take the derivative of this once, and it just brings it down to 4 dt and a 2. And you take the derivative again, and you get another term, because then there's an x. Sorry, this brings out a 2x. So this gives you 2 terms because there's 2 terms. This gives you 2 terms because there's a second derivative. And you see that the 2 things are equal to each other. Relatively painless. Does anybody have any questions on this? So that's what I was looking for. Not everybody did it this way, and so there are several solutions that other people came up with that I gave full credit to. If you derived this, several of you derived this from not first principles, but close to it. So several of you derived that. I take that as fine because I figure that's going up the mountain the other way. Does anybody have any questions about this part? Everybody good? 2, show that average x squared goes like 2 dt. So the average of x squared is equal to the integral of x squared times n of x and t dt. Really, you got to normalize it by the mass, but we'll just pretend that it adds up to 1, right? I don't think anybody got hung up on that, but that's all right. So technically, you probably need to divide by the integral of n of x and t dt. But if n integrates to 1, we'll say that the total mass in the box is 1. Then this integrates to 1, and I can ignore that term. So we got this integral to do, and this is the integral of x squared over, let's take that outside, 1 over 4 pi dt, square root of that business. So that goes out front because it's not an x. Then I've got x squared e to the minus x squared over 4 dt dx, and we're going to integrate from minus infinity to infinity. So there are several ways to do this integral. I hope that everybody kind of has an idea of how to do it. So the way you do this integral is you treat this like, you put an extra constant here, we'll call it a. And then I say, I know the derivative of this, e to the minus x squared. I know this integral. Then I can just change variables, or I can take a derivative of this with respect to a, and that brings down an x squared, and then I've got my x squared. So that's basically how you do this integral. How do you actually do this integral? You plug it into Wolfram Alpha. So several of you said, I plug this into my integral thing, and I get this answer. here, that's perfectly, this isn't a calculus class. So you do this and you get all the answer works out that the average x squared equals 4d2 dt. There's not a pi in there, is it? No, just 2dt. But I want 2. Okay, the 2d doesn't matter. The t is important. The fact that this is t to the 1, this is linear in t, and this is x squared. So this is the mean squared separation, the mean squared distribution, increases linearly with time. And that's the important bit about diffusion processes. Questions? Everybody happy? And then the last one, pretend this is a heat equation. So I'm going to heat a rod in the middle of the rod. So here I've got a long rod and I'm going to light a match. That's the best lighter I've ever drawn. So I put some heat source in the center of this and I heat it up and then I let that heat spread out. What's that look like? So it looks first like a delta function. And the delta function, you can treat that as a very narrow Gaussian. And then it just spreads out over time. And you can see that that's what this does. That's what this equation tells you to do, is make a Gaussian, make it spread out over time. So this equation, so a Gaussian is e to the minus x squared. There's other stuff on it too, but that's the important aspects of a Gaussian. So how do I plot e to the minus x squared? Well, okay, at x equals 0, this equals 1. Now, okay, there's crap in front. There's other crap, so okay, it's not 1, it's that crap in front. But for my graph, it's 1. And then it falls off. It falls off the same in both directions because it's squared. So the plus side is the same as the minus side. So this is squared. So it falls off in both directions. Kind of smoothly goes down to infinity. So this is what a Gaussian looks like. And it's got some width. But my width now is now 4 dt. So as time goes on, the width gets wider. And because we have the same amount of mass or whatever, the amplitude goes down too. The height of the center goes down. You can see that the height of the center goes down too by this bit out front. So now the graph in front shifts how high the center is and how wide it is. So it should diffuse like this. The peak goes down, the moment gets wider. You should have something that looks kind of like that. Does that make sense? This is mostly an exercise in plotting some Gaussians. Spend a minute thinking about what a Gaussian means. So what are the important parts? So a Gaussian has 2 important parts. Well, okay, there's the minus x squared, and that's what does it. Really, a Gaussian has 3 important parts. Let's just take a minute. So if I have, like, the most general form of a Gaussian, it has some normalization, and that's what keeps it integrating up to 1. But that's going to change. It's got the mean, and that's just where, to the left or to the right, the center of the distribution is. And it's got a width, which is the denominator of the thing in the exponent. That's how wide the distribution is. So this one goes up with time. The amplitude goes down with time. The mean doesn't change. So almost always you can shift to a system with 0 mean. It's almost always a thing you can do. Okay, the first one, that's good. Any questions on the first one? Let's see. Derive an expression for the convective derivative of vorticity. And here, what I'm looking for is, so you can start and hit this one. I realize that if I want a particular derivation, I really always gotta say what I want you to start from. Otherwise, people start from random places. But here's what I was looking for this one. And if you did something basically right, but got up the tree, but didn't do it this way, that's okay. So we start with d omega dt is del cross b cross omega. Several of you derived this, which wasn't necessary, but I appreciate because I get to see that you know how to crank through the equations. So we just use there's a vector identity for this triple product or this double derivative. So this is basically, it's the derivative of the product of things. So you've got to use the product rule, kind of, but because it's all vectory, you've got to use this other vector identity, which goes like, okay, there's a v dot grad omega, and an omega dot grad v, and a div omega v, and a div v omega. Now the signs. How do the signs work out? That's minus, that one's a plus, that one's minus, this one's a plus. These two both go away because we have div omega, which is the divergence of a vector field, or of a divergence of the curl of a vector field, and the divergence of the curl goes away. That's nice. This one, div v is 0 because it's incompressible, which did I remember to say that initially? I should have said incompressible explicitly, but anyway, a lot of people did that. So that one goes away. So then we're left with these two terms. This one is part of my convective derivative. The convective derivative, remember, and here I apologize on behalf of everybody who does hydrodynamics. This convention is a little, the nomenclature and the terminology is kind of ambiguous, and people use different terminology depending on who you are and where you came from. So one way to write this is often written as with capital D, and this is equal to partial Q partial T plus V dot grad Q for any quantity Q or function or whatever. So for any Q, this is what the convective derivative is. Now I typically write it as just little d, 100% equivalent. That's the same thing. It's just this. People started using this big D when they were doing hydrodynamics to really emphasize the fact that this is the full derivative, and you've got this v dot grad. So this is part of that. So this goes to the other side, and I'm left with I need that space. Wrote that crap there. This goes over to here, and we're left, as the right-hand side becomes d omega dt, and then the left-hand side is just omega dot grad v. And then everything else goes away. So you're left with this relatively simple expression. Anybody have any questions on that one? Derive the Reynolds stress. What does it represent? So, when I have Navier-Stokes, or let's write the momentum equation. Oops. That is not just a rehouse, thank you very much. Past me, sabotaging my equations. So what we do is, okay, rho is constant, because once we entered the turbulence, everything is incompressible. That'll go away. It's probably going to be incompressible for the rest of the semester. I don't think I'm doing anything explicitly compressible. So density is constant, so we could it's just a decoration. So what we want to do is we want to replace V equals V bar plus V prime. And to be fully explicit, we should probably do it to both terms. So here we're taking a mean equation and a fluctuating equation, or a mean component and a fluctuating component for both the velocity and the pressure. So what we're going to do is we're going to plug these into here, and we're going to average. And we're going to use the fact that Q prime bar equals 0 and Q bar bar equals Q bar. This one feels kind of dumb, but it's important to state it. And this one is important, even though it also feels kind of dumb. And you can see that these are true just by taking this. If I take the average of this, I better get V bar equals V bar. And and this one's got to go away. So we plug in here, and we plug in here, and we plug in here, and we plug in, let's get rid of this term. It all goes away. So we plug everything in, and we take the derivative, and we're left with, we're left with d rho v bar plus v prime plus div rho v bar plus v prime, v bar plus v prime plus p bar plus p prime delta ij, and then we'll kill the viscosity for now. And here we are with my parentheses, and this equation equals 0. It all equals something. So here I've just plugged in my mean and my fluctuating. Now, for the first half of the term, we would throw out all the fluctuating squareds, but we're not doing that now because the fluctuatings might be very large. So we do this, and now we take an average of everything, and we're left with d rho v bar, this term goes away, plus, let's expand this out, we got v bar plus v bar v prime plus v prime v bar plus v prime v prime. This is ij, 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 ij. So these are both i's and these are both j's. That part's important. Not a lot important, but. So then I get these two i's and j's. And then I'm going to average that. So this one, both of these are already averaged. So they just come out. I'm left with div rho v bar, v bar, v bar. This guy goes away because the first term is constant with respect to the average, and the second term is 0 with respect to the average, and the same time with this one. So these two guys both go away. And this lady at the end is v prime ij bar. And then plus this term, the second one goes away, we're just left with p bar delta ij. So now the stresses are the things that are in here. And the Reynolds stress is the new one. So this looks just like the equation that we started with, but for this new term. And what this new term represents is fluctuating quantities interacting with fluctuating quantities and affecting the mean flow. So it's so we have this mean equation. This is an equation for the mean velocity, which, in a real world would look just like the regular equation, but it doesn't. It's got this extra production term. Any questions on that? Yeah.
I have a really quick question. So if q prime bar is equal to 0, why is the vi prime vj prime big bar not equal to 0?
So that's a good question. Let's see. What's the best way to answer that? Let me take a second to formulate a good response. So I'm just going to erase all this. I'll write it up again if anybody needs it. But. So we got. So any average is an integral, really. So you can think about it as just writing down an integral. So this is the integral of q with respect to something. It could be ensemble, it could be time, it could be space, it could be something. You've got to average with respect to some quantity, but it doesn't matter for our purposes here. So let's just say we're averaging with respect to time. But I can change that. And maybe there's a 1 over normalization up front, but we can always set that to 1 and we'll be done. So when I've got a quantity q, and I'm going to write it down as q bar plus q prime. Q bar we've defined as is the integral of q dt. So q bar doesn't depend on time at all. So when I take the integral of, so when I get q bar bar, that's the integral of q bar dt. But q bar doesn't depend on time anymore. We've averaged that out, right? I've already done that integral, so there's no time component in here. So this is just q q bar times 1 over dt, which is what? Realistically, I need my 1 over big delta t out front. So that's just going to be 1 over big delta t, so that's just, sorry. This part is just 1, so we're just left with q bar. When I have something like q bar q prime, let's actually explicitly show this second one. So if I have q prime, and I take the average of that, that's equal to the integral of, let's write this as q minus q bar dt. Does that make sense? So this is the integral of q minus q bar, and that's just equal to q bar minus q bar, which is thing minus thing, which is 0, always 0. So now, just get myself some real estate. So what's up with q prime I, q prime j? When I take the average of that, that's equal to the integral of q prime I, saying one thing, writing another, dt. I don't have anything that I can take out of the integral here. So there's no reason for me to say that any of these guys equal 0. I can say that this guy equals 0 because I can just show it. It's equal to the thing minus the thing. It's got to be 0. But I don't have any stunts that let me take this out of the integral, and I don't have any stunts that let me take this out of the integral. And if you think about one limiting case, if you think about where I equals j, then this is the integral of q prime squared dt. And that's strictly positive. It's only 0. If you've got the integral of a square thing, it's only 0 if the thing is 0. Does that make sense?
Yeah.
So the square one is the one to get your intuition shored up. The square one is the one to think about, as that's where you can really see that this thing isn't 0, because this is the sum of a bunch of positive things. That's a very good question. Thank you. More questions? Everybody good? Let us talk more about what's next. Turbulence. The turbulent cascade. So we do the turbulent cascade twice. Once with thinking, and that's a long problem, and once with math, and that one's very short. So okay, the first one. So I have a pot, and I stir up a pot, and I look at where the energy is as a function of scale. So first off, does the energy cascade to bigger scales or smaller scales? Smaller scales. Oh, did I skip a problem? Oh yeah, I skipped number 3. Let's back up and do number 3. I need that one. Number 3 is about vortex tube stretching. So we started with the convective derivative for omega. So we got d omega dt equals omega dot grad v. Now there are 2 solutions to this that are basically the same but actually very different. So the first one doesn't need this at all. The first one says, well, okay, so they both start with the same argument. One, things move apart. That's the argument. That's an important thing to say first. Why do things move apart? Well, when you have a chaotic fluid, statistically 2 things are going to move apart. Or if I take one velocity and another velocity, the phase space of velocities where they're moving away from each other is larger than when they're moving towards each other. I wanted to sit down and prove that this morning, but I ran out of time. But statistically, things move apart because random or phase space. So this is an important part of this proof that a lot of people missed. Why do things move apart? Things move apart because if everything was moving together, my fluid would collapse to a point. That doesn't make any sense, right? So things tend to move apart. Now, 2, why does that mean things get smaller? So you can either use conservation of mass or what's his name? Kelvin. Thank you. Or you can use so you can either use conservation of mass or Kelvin's circulation theorem. And both of those say omega times A equals constant, where A is an area. Now maybe not omega, maybe this is L. L times A is a constant. It's conservation of mass. Makes sense? So if I have a little parcel of fluid, the volume of that fluid has got to be conserved because the density is the same and the mass is constant. Or the density is constant, so mass has to be the same in that parcel of fluid. Or omega times A is constant, and that's angular momentum conservation, and that's Kelvin's vorticity theorem. Either of these is fine. We know that both of these go up. So L goes up because things move apart. That's my argument. Omega goes up. This is a little more complicated argument. Omega goes up because things move further apart. That means V is probably positive. Grad V is probably positive along omega. So that means this term is positive, which means that d omega dt is positive, which means omega goes up, which means A goes down. That makes sense? So your fluid dynamics is like this vortex tube stretching because it's more physicsy, but conservation of mass gets you there with the same math. So L and omega increase, so A, which is the size, decreases. So things go to smaller scales. Now this breaks down, and it's not a great argument if you want to talk about like turbulence on the surface of the Earth, which is basically two-dimensional, because things go to larger. Some things go to larger scale, not everything. The vorticity goes to larger scale. The energy goes to smaller scale. Weird problem. Okay, anybody have any questions about vortex tube stretching? Good. Okay, now we'll talk about the cascade. So things move to smaller scales, as we've discussed. Structures move to smaller scales. Energy moves to smaller scales. That's A. B, discuss the 3 regimes of this cascade and what physical processes dominate each. I'm going to do this so I've got energy versus K versus wave number. The reason that I like using K is because I like thinking about things in Fourier space. Fourier space is very handy. So we've got the large scale, we have injection. At the small scale, we have dissipation. And we have a decay of energy. So there's maybe something slightly larger than where you're actually dumping it. There is math on how this falls off, but we don't really need it. You can skip it for now. And this kind of rolls off like that. And there's physics that you can put in there, though not nearly as much physics on this as I want there to be. I really need to understand this really in a high level of detail for some research that I need to know that I'm trying to do, and the detail does not exist in the literature, and it makes me sad. So there's some questions about how things actually dissipate. What do those structures look like? How many of them are there? How big do they get? But and then in the middle is the inertial range. And we can think of this as the competition between the v dot grad v term, that's a headache, and the nu del squared v term that dissipates things by the Reynolds number. So when things are large, this term wins. This is the inertia term. And when things are small, this one wins. That's the dissipation term. Now if we draw this with length, okay, when you draw this with length, the only thing you really need to do is flip the axis, so this should look like this. You shouldn't have more energy dumping in here or anything. It should just look like this one, but backwards on axis. The only reason that I do it this way is so that we're talking about K and L and how K is 1 over L. What that means for the axis is you just flip it. Why? Well, we're logarithmic. All these plots are logarithmic in both scales, so A goes to minus A is the same as A goes to 1 over A, right? That does make sense. Maybe not. Maybe don't think about it too hard. So because this is logarithmic, going from K to 1 over K is just flipping the axis. It's just a minus sign. So okay. And then was there any other questions up there? Okay. So the second question is derive the 2/3 law, which is the slope here. So what's the slope of this line here? This goes like L to the 2, nope. V goes like L to the 1/3. Why? So the energy dissipation rate is V squared over time. We're arguing that we're in steady state, so clearly this can't depend on time, so I need some other time. So that time is going to be length divided by velocity. So really the argument is dimensional analysis. It's the only thing it can be, because that's the only free parameters. So this equals V cubed over L. Several of you skipped this eddy turnover time business and just went straight for V cubed over L. Perfectly legitimate, because that's what the dimensions tell you. The dimensions say that it's got to be V cubed over L, and that's it. Now we can argue that it's got to be V squared over time. This is the physics argument. But because the dimensions tell me that it's got to be this, that tells me that the time has to go like that. So dimensions tell me this. And because we're in steady state, this is constant. So V goes like epsilon L to the 1/3, 1/3, or V squared equals L to the 2/3. So that means that the relative velocity between 2 points gets bigger as you go to larger and larger scales, up to a point. If I'm past this scale, then I've got just a diffusive process. And things will just push me around. So it's not going to, so the relative velocity is random and has 0 mean once you're beyond the inertial range. And that's a diffusive process, which I'll talk about in the next problem. So derive 2/3, everybody's good to do that on the final. L squared. So I think it actually works if you do it this way. So V equals L to the 1/3. And if we say that this is dl dt, I did it with a square before, but I think that it works if you don't, I don't think that you actually have to square it, because I'm implicitly doing the RMS in my head. So dl dt is L to the 1/3. If I move this over here and that over there, I get L to the minus 1/3 dl equals dt. And I integrate this, and I'm left with L to the 2/3 equals t, or L squared equals t cubed. I just cube both sides. I did it in a more complicated way before, but this way works better. The reason I did it in the more complicated way is because that's how Paul Davidson does it in his magnificent book on turbulence, which is like this thick and weighs like 5 million pounds. And it's this gorgeous glossy paper. It's a really great book. But this way works just fine, right? I didn't do anything stupid there. Aside from the fact that it's a signed quantity and really you can't do it. But so we get to this this result. L squared goes like t cubed in the inertial range. So when this is true, this is true. And this is true in the inertial range. This is when you're away from the force and away from the dissipation. And then the last one, I throw 2 bottles into the ocean with messages in them now. And at one point in time, the messages had jokes on them, but I decided that none of the jokes were ever funny, so I dispensed with the jokes. So what happens? So what I tell you is the correlation length is 5 kilometers. And they start off 1 meter apart. Now, I didn't have many problems on the correlation length explicitly. But we did talk about it a bunch. So what is the correlation length? In this turbulent cascade, the correlation length is kind of on the same size as the integral scale, as the injection scale. What's the integral scale? I didn't tell you what that is. We'll just talk about it like the injection scale. We could talk about that like the correlation length. It's a lot of things that are different, but not a lot different. Things that we don't really, the differences that we can talk about, but they're confusing and not worth it. So this scale here is the injection scale. It's also on the same order as the correlation length. So if I'm way above the correlation length, then two particles, let's talk about x squared, are going to separate like t. But if I'm way less than the correlation length, which I am, then x squared goes like t cubed. Or v goes like L to the 1/3. So this is the important bit. Several of you got here and then said a whole bunch of other stuff. I'm like, yeah, just stop there. This is what I was looking for. So because they start off with a separation that's small compared to the inertial range, then they separate like the 1/3 law. Does that make sense? So now one question that I like to ask on the final is, say I start off with 2 very small beads of plastic and I drop them right next to each other in the ocean, what happens? Eventually they'll be on the opposite sides of the planet, but how did they get there? First off, when they're very close together, they separate by molecular diffusion. And then they separate by, when they're very close together, they're going to move ballistically because they're just good. So they'll separate by molecular diffusion when they're molecules apart, but that doesn't last very long. Then they're separated ballistically because they're not in the cascade yet. They're in this inertial range. Then they get picked up by this cascade. Once they're beyond the dissipation scale, then they get picked up by the cascade and the velocity separates very quickly. Then beyond the inertial range, they're separated by diffusion. So the separation goes like t instead of t cubed. And the velocity difference, I think, is random and uncorrelated. Does anybody have any questions with this one? This one threw everybody off. So don't feel bad if you got here and were like.
I have a question.
Yeah.
Could you please go over again how you went from average of x squared is kind of t, and then average of x squared is kind of t cubed?
Yeah, this is what we just did. And I called it L squared goes like t cubed before. So this is the same thing. This is true when you're in the inertial range. So this is true when v goes like L cubed. When you're above the inertial range and you're large compared to the turbulent fluctuations, then the velocity difference goes like t. And this is what the book did. So the book does this and calls it turbulent diffusion, and that's accurate, and I'm into that. But it's only turbulent diffusion if the structures that you're looking at are bigger than the injection scale. They're bigger than the integral scale of the turbulence. So this is true when you're large compared to the injection scale, and this is true when you're small compared to the injection scale. That was a good question, thank you. Any other questions? Everybody good? All right. Okay, new stuff. Now I'm gonna stop the video and start a new video. Okay, do I have enough time? I do, okay. Let's see.
Oh, here.
Yeah.